Okay, I forgot to record part of the class, so I guess I just will repeat a little bit. And basically, we just before that, we looking into the Dirichlet distribution, and we try to compute the mean and the variance. Like basically for the Dirichlet distribution, we have like hyperply parameters like alpha 1 up to alpha n, and the variables are x1 up to xn. So this is like probability. So therefore, like x taking values like xi will take values from 0 to 1. So within the range 0 interval 0 to 1. And so we compute the mean and we compute the variance. Like basically we can compute the second moment, then we can compute the variance like this one. Now the mode, like I'm not going to compare it, like it's just a simple exercise. You can take derivative of the distribution. Like I'm set to 0, you'll find that the mode is actually equal to this guy here. And then let's say we have now a kind of likelihood with a multinomial distributed likelihood. So as we mentioned, this is a dice example. So therefore, like we have 6 different outcomes. Like each outcomes can be different. So we assume the dice can be biased. So Q1 and up to Q6 may not be equal to 1 over 6. And then like x1 up to x6 is like how many outcomes, how many ones and how many two, how many three, and so on, so forth that occurs. So therefore we have, I guess I've written down somewhere, say, yeah, x1 sum plus x2 plus so on up to x6 should be equal to n. N is the total number of tossing the or throwing the dice. So this is the likelihood, and the conjugate pi, as we just mentioned, that is a Dirichlet distribution. So let's say we have some hyperparameter alpha 1 up to alpha 6. So Dirichlet have this form where basically say q1 to the alpha 1 minus 1 and to q6 alpha 6 minus 1. And for multinomial, have a form like this. So multiplying these two is extremely simple. Right? You see, like I can just group this exponent together. So therefore, q will become, for the exponent for q1 is like q1 to the power x1 plus alpha 1 minus 1, and so on and so forth. So therefore, like if you look at that, this is actually just a Dirichlet. Now with like the parameters updated to like alpha 1 plus x1 up to alpha 6 plus x6. Now, if we want to do a Bayesian estimation, then basically we want to take the average, take the mean of the posterior. For example, like we want to see like what's the probability that in the future we get or what was the fraction of 1, or basically what's the probability of getting a 1. So using Bayesian, we'll be just taking the expectation of Q1 that we computed earlier for Dirichlet. The mean is just equal to the sum, it will be just equal to alpha 1 plus x1 here over like the sum of all the parameters. So therefore it will be like alpha 1 plus alpha 2 plus alpha 3 up to alpha 6, and x1 plus x2 and so on plus up to x6. Here alpha 0 is just the sum of like alpha 1 up to alpha 6. Here is a shorthand notation we used here earlier. And so that's basically a very simple kind of inference for multinomial likelihood and also Dirichlet prior. Now we look at another example. Let's look at another example that have a Gaussian likelihood. And in this case here, it will say it's just a scalar Gaussian. Let's see, is that so? Yes. And only have one observation like x here. And say the mean is equal to mu. Now we want to kind of approximate the mean mu here. And here we assume the variance is fixed. So I kind of emphasize here by using this semicolon here. So after this bar here, the x here is like a variable, but after a semicolon here, this is like the parameters. We assume it's fixed, so we're not trying to estimate the variance here. Instead, the variance is fixed here. Now this can be decomposed into actually this is not equal, but it's kind of proportional to the likelihood x given mu times the pi is a p mu theta. Here's like we want to look at for another conjugate pi of this Gaussian distribution, right? But note that like it's important to see like what parameter we are estimating. Here we are kind of fixing the variance and like trying to estimate mu. So if we trying to do the reverse, the conjugate pi, as you will see later on, will be different. So then if we write down the form for this guy, because we're estimating mu, we just care about like the part of the PDF that has mu there. So that should have a 1/2 pi sigma square, right, somewhere. But since this does not depend on mu, we just ignore that, and we can group them together into some constant here. And so in that case, the conjugate pi for this guy, as you can see by inspection, will also be a Gaussian. So let's say we can pick a Gaussian with mean mu naught and variance sigma naught square. So in this case, the parameters here is basically this theta here is this mu naught and sigma naught square. And in general, we don't need to have like sigma and sigma naught square to be the same. Now this would be basically a multiplying two Gaussian distribution, right? By this time we should be quite familiar with this thing here. So the expression for this one, the equation for this guy, basically the new variance or like the new position will be just the sum of the position. So therefore the new variance will be the inverse of 1/sigma 0 square plus 1/sigma square. And then the new mean there will be just a weighted sum, weighted by the position for this guy. So the position for this one is like 1/sigma square, positions for this one is 1/sigma naught square, so therefore it's x over sigma square plus mu naught over sigma naught square, and then so it's weighted sum, right? So we will need to normalize that, have this over divided by 1/sigma square plus sigma naught square, sigma naught square. And this will be the posterior distribution, right? And if we want to do a Bayesian estimation, in this case, whether we use Bayesian or map will be the same, because like for Gaussian is symmetric. The mean is basically the same as the peak, as the mode. So therefore, like in this case, we want to estimate the mean is basically just this guy. So if we want to do an inference, say we have some prior given by this, like with mu naught and sigma naught square, and we have the likelihood like this, and my oscillation of x, then basically the estimate of the mean is basically just equal to this. Maybe I'll write better, is like x sigma naught square plus mu naught sigma square over sigma naught square plus sigma square, something like that. Now let's look at another example. As I mentioned earlier, we can, if instead of like trying to estimate the mean and fixing the variance, maybe we can do the reverse. So in this case, we are fixing the mean, but we are going to estimate the variance. Or more precisely, I'm not going to estimate the variance here, but instead we'll estimate the position. So basically 1/sigma square. And then we can write down the form here. So again, like this is basically this posterior will be proportional to the likelihood px given lambda here, with mu here is fixed, so I have a semicolon, I have mu afterwards, so just indicate this is a parameter, so it's fixed, and then multiply by prior p lambda here. So now let me write down this PDF in terms of the mean and also the position. So we have a form like this, right? I mean, in this case, be careful, I cannot discard this, because I can discard the square root of 2 pi, but we cannot discuss this square root of lambda, because lambda. Now the precision is the variable. And now we want to look for this to match with this form, right? But before going for that, like we want to look at a more general case, like what forms we're supposed to have when we have more than one observation. Because we just look at this, it looks like we need to have a form have like square root of lambda always, but it's actually not that case. So let's look at like if we have like instead of one observation, if we have n observations here, and now then if we compute the posterior will be proportional, or like I can write equal to a constant that doesn't involve like lambda multiplied by p lambda the pi, and also the product of this likelihood. Here we use the Markov property, right, given lambda here, so it does not depend, it only depends on lambda basically. And this guy is equal to this, right, square root of lambda exponential this guy, and basically this is equal to this one here. Now then p lambda, I still keep p lambda here, but here like I plotted like from 1 to n, so therefore you have lambda n over 2 here, and here I have exponential minus basically this product here I can get into the exponent and become a sum, so therefore it become like minus lambda sum this guy here. And then finally let's see, yes, for this guy I need to look for a distribution conjugate pi to this guy, right? So I want to look for something have the same form like this guy. So what we want will be something like lambda to the power something and then exponential into some lambda, right? And it turns out the distribution for this guy will be a gamma distribution like this. So I say have a form like lambda to the some parameter a minus 1 and exponential minus b lambda, and the normalization factor will be like this, like 1 over gamma a times b to the a. So again, like knowing the PDF here is very easy to compute the mean. It is the same trick we have used for this this lecture here. So for example, if I want to compute the mean of gamma, I will have, this is the PDF. Let's see, right, PDF a minus this, I'm just copying from above here. And so this is an expected value of lambda, so I should multiply by lambda here. But then this lambda, of course, I can go into here, so I have like lambda to the a instead, like this one. Now this guy here, I can pull it out, it's just a constant, I put it out here, and then I will only have this part here, right? I have if I just erase this, we write this again. So I have like b to the a pull out, gamma a also pull out here. Now I integrate over lambda a exponential minus b lambda d lambda here. But now note that like this is very much similar to the gamma PDF here, right? It's actually correspond to a gamma PDF with parameter a plus 1 and also b, right? Because I originally like for when the parameters is a, actually this should be lambda a minus 1. So now this is lambda a, so therefore the parameters should be a plus 1. And we know that like, so if we take integral this guy, if we also have this normalization factor, integrate the whole thing will be equal to 1. So therefore if I integrate only just this part without the normalization factor, should be just equal to the 1 over that normalization factor, right? So therefore should be this one should be just equal to gamma a plus 1 over b to the a plus 1. So maybe I copy here, gamma a plus 1 b a plus 1 here. So then I cancel this b to a, and I only have b left here. in the denominator. And for this guy, gamma A plus 1 again is equal to gamma A, or A times gamma A. So I guess gamma A got cancels, and therefore it's just equal to A over B. So then okay, with this, then we can do a Bayesian estimation, right? Bayesian inference, right? Now, for example, if we have what is described here, we have like n observations like this, and let's say I have just that conjugate prior, the parameter for the gamma distribution is exactly have A and B here. So then if we look at the posterior, let's see where is the posterior. Okay, go back to here. So let's say our gamma have this. Okay, this is a little bit ugly here. So let me erase this. I don't need this anymore. So let's say this is my gamma prior that go into this guy here. So this is the p lambda is equal to this guy here. So then if you look at this one multiplied by this one, I don't care about those normalization factor, those constant here. I basically have lambda a minus 1 plus n over 2, and then exponential minus lambda b plus this guy here, right? So then if you look at this, what is this? This is basically a gamma function with a parameter is a plus n over 2, and the variance, sorry, not variance, the b parameter is a b plus this sum over x minus I minus mu square over 2. So then if we do a Bayesian inference to estimate the lambda, so the final result will be basically equal to this. It's just A over B, right? So therefore it should be like A. This is so, maybe erase that. So it's like A plus n over 2 over B plus like sum over I from 1 to n xi minus mu square over 2, something like that. And we can look at some special case. For example, like if we have A equal to 0 and B equal to 0, I'm not sure that that's a valid parameter because 0 is constant. It may not be okay, honestly. Yeah, but anyway, like that's the result for in general. If we're trying to estimate lambda with the gamma prior, and also a kind of Gaussian distribution, but with like mean fix. So okay, I guess I have okay, so I guess I can stop here actually.